Methods of variance reduction in Monte Carlo methods. The topics that we will go over in this video include an introduction to variance reduction in Monte Carlo methods, the importance sampling method, and the control variance method. Section 1, Intro to Variance Reduction. We have seen that in simple Monte Carlo integration, we can obtain an estimate of the integral of the function g of x through using an estimation of the expected value. Expected value of g of x is equal to real integral g of x f of x d of x, where f of x is a density function. If we then draw a random sample x1 through xn from f of x, then the mean value of the g x sub I variables estimates the expected value of g of x, and this mean converges to the true value of the integral with probability 1. There are many different ways that we could improve this process, including increasing the efficiency of the estimation. This means finding ways to reduce the variance of our sample mean estimator. One way to lower variance is to take a greater number of draws from the f of x distribution, but this requires a large increase in the number of n draws that we would need to take for a rather small reduction in variance. Section 2, Importance Sampling. A more efficient means of improving our estimate involves improving the distribution which our random samples are drawn from. If we want to find the integral g of x dx, and we have a random variable x with function f of x, then the expected value of their ratio, expected value of g of x divided by f of x, is equal to the integral of g of x divided by f of x times f of x dx, which is also equal to g of x dx. This expected value of the ratio can then be estimated as usual through Monte Carlo integration, taking the mean of the ratio g of x sub I divided by f of x sub I, where x1 through xn are generated from f of x. F of x in this case is referred to as the importance function. It can be seen that in this case, the variance of our expected value is variance g of x divided by f of x divided by n. This variance is at its smallest when g of x divided by f of x is near constant, where the ratio of g of x and f of x is near constant over the interval of interest. When f of x is close to g of x in this way, the variance is much smaller than in simple Monte Carlo, which has variance g of x divided by n. Now for an example. Let's use both simple Monte Carlo and Monte Carlo with importance sampling to estimate this unusual integral ln of 1 plus x divided by x. From simple Monte Carlo, we can see the results from our R function. This is the same process as we saw before in the previous video on simple Monte Carlo. For importance sampling, we need to choose an f of x that will be reasonably easy to generate draws from, and whose ratio with g of x will be near constant over the interval. We choose this f of x, which is simply the function e to the negative 1/3 x, truncated to the interval 0, 1. It can be seen from this plot that this function follows g of x very closely. In our R code, we generate random samples from f of x by using a uniform sample and the F inverse transformation. One can also note that the simple Monte Carlo is actually exactly the same as importance sampling, with an importance function of 1. Comparing the histograms of our simple Monte Carlo estimator versus our importance sampling one, the variance of the bell curve for our importance sampling estimator is drastically reduced. Comparing the exact standard deviations of both of our estimators in this case, we can see that the importance sampling resulted in a standard deviation about 1/10 that of simple Monte Carlo, and the percent reduction in variance turns out to be about 98%. We see that importance sampling can be a pretty effective method for variance reduction. The biggest obstacle for this method is finding an appropriate choice for f of x in the given interval. Section 3. Control variance. Another method of improving Monte Carlo integration involves finding a function f of x that is highly correlated with g of x, and for which we will know the value of mu is equal to expected value f of x. We now have a new estimator that we will call theta c. Theta c is equal to g of x plus a constant c times f of x minus mu. It can be shown that theta c is an unbiased estimator of expected value of g of x, which is why we are able to use theta c as our new Monte Carlo integration estimator. It can also be shown that the variance of theta c is a quadratic function of the constant c, which we can find the minimum of at a point that we will call c star. And thus the minimum variance of theta c is variance g of x minus covariance g of x f of x squared divided by variance f of x. The function f of x is called a control variate, and it can be seen that the reduction in variance from simple Monte Carlo is exactly covariance of g of x f of x squared divided by variance f of x. Thus, the higher the covariance and correlation between g of x and f of x, the greater the reduction in variance will be. The value of c star is also dependent on covariance g of x, f of x, and variance f of x. In order to compute theta c, we will need to find an estimate of c star through using a preliminary Monte Carlo estimation of these values. Now let's see an example of Monte Carlo with control variates. We'll estimate this integral using simple Monte Carlo and Monte Carlo with control variates and compare the results, same as we did with importance sampling. This integral may look pretty nasty, but it is monotonically increasing on 0, 1, so control variate as simple as f of x is equal to x is an appropriate choice. We see that they have a very high correlation. We'll next find the estimate of c star and the value of expected value, f of x. We can find an estimate of c star by simply taking uniform draws and using them to estimate the value of covariance g of x, f of x, and variance f of x. Expected value of f of x in this case will be the integral of x and its distribution function, which will be a uniform 0, 1 distribution. This results in expected value of f of x is equal to 1/2. Performing the control variate MC process in R is then as simple as plugging in our values for c star and expected value f of x, alongside the mean of f of x and g of x. And here we again see the results compared with simple Monte Carlo. The distribution of our MC estimated with control variate has a much, much narrower range of variance. And we can see that the standard deviation of our control variate estimator is again about 1/10 that of our simple Monte Carlo estimator, and that the percent reduction in variance is about 98%. So, control variates are also a very effective method to reduce estimation variance, provided an appropriate f of x function can be found. In conclusion, this was just a brief introduction to variations on the Monte Carlo methods that can improve estimation efficiency. It shows how versatile the Monte Carlo procedure is, and how a powerful mathematical tool can be made even more powerful with just a few tweaks.